Okay, we're soon going to start with our last talk. Our last talk is a bit different. We're going to hopefully play games. So let's see what Bitbox is.
Okay. Well, thank you. Hello, everyone. I would like to present you the Bitbox. So I will run the presentation from the small console itself. So I hope everything is all right. And I will take the different slides through my gamepad. So the Bitbox is a do-it-yourself project, a personal project that is now currently being made with several other people. It's a hardware and software project. So what's the button? That's this one. I will first introduce you what were the goals to present what I wanted to do with the Bitbox, to have a general presentation of what it's capable to do, how it relates to other small video game consoles, because it's about video games. Then a hardware, how is a hardware design and what's inside it. And then the different levels of software. You will see the architecture is quite simple. Well, first, the goal was to make a modern, do-it-yourself, and simple video game console. Modern, not in the sense that, not in the Xbox modern style, but in the modern style that you wouldn't have to try hard to find peripherals, for example, to find cartridges, etc. The idea was to keep the environment quite modern with SD cards, for example, with USB gamepads, etc. But to play all the games, maybe, because it would need to be do-it-yourself, so anyone could be able to do it in his attic or in his own house without any particular tools besides a small soldering iron, for example, and be able to source the components without having to build hundreds of thousands. So simple to build, simple to program. So everything is been special case, of course, nothing is portable, and that's part of the fun. There is no operating system, everything is very simple, and keep it simple from start to finish. And it's still a video game console with games. So retro gaming means old school, meaning for me a nice, simple, and fun type of games, which we could be able to reproduce with an in-house made hardware. The do-it-yourself hardware is generally low spec in order to be able to build it yourself, to solder it yourself. So using retro gaming type of games, of course, which one is perfectly natural. There are many people who are trying to do emulation or trying to replay on games on real hardware, but they're quite difficult to find or to maintain. For example, those old Atari or old Amigas or old Nintendo can be difficult to find or to find peripherals for or to repair. Software emulator are maybe not the real deal because you're seeing small different glitches and you don't have the feeling to have, well, you just have a computer with some very nice games on them, but it's not the same thing exactly. And there are hardware emulator. For there are, you don't see very much, but there are older, well, new, old Atari ST or recreation with FPGA, well, washer drive, level hacking, but sometimes used to reproduce bugs, which is a bit of a shame to put so much resources, intellectual uses, just to reproduce some past design, because it would be simpler to just throw everything. Well, that's one of the principles, throw everything and just start from scratch and whatever. One of the interesting elements was to code in the retro way, meaning no operating system, direct hacking of the hardware for different graphics, have a fixed hardware, and try to code and try to find what you can do with this, but having a fixed hardware. I put no frameworks. There is, well, you just have the URC compiler, and the first byte that you execute, and you write everything that will be executed in your game. So there is a direct take on the material and the hardware, well, which is quite different from the modern kind of program. So my goal was to emulate 16-bit like console or 16-bit era computer kind of games. Well, you can see here on the left well, it's quite blurry, but the Zeldas and Metroids in the 8-bit or 16 bits. Well, I wanted to emulate or to replicate maybe the 16-bit look and feel, because I think it's better graphically and not too complicated to do. Well, possible at least. I wanted it to be as simple as possible, as I said, and to be able to play on a TV, because console games are played on a big TV, not like your Nintendo Game Boy things. And of course, everything is in the open. So the toolchain is completely open. There is no binary blob driver, unlike, for example, the Raspberry Pi, which is an awesome board, but which you can't replicate in your house. You cannot buy the chip. You cannot, except if you buy, I don't know how many hundreds of thousands by Broadcom. It's very difficult because it's a 4-layer PCB. So everything, I wanted everything to be simple and completely open, of course. So as well for the code and the hardware, the hardware design. So to keep it simple, the idea was to have only one chip, so no external memory, everything in a microcontroller. So a bigger microcontroller than the one you can find in the Arduino, but only one microcontroller with everything inside. No FPGA because it can be quite expensive. It can be quite tricky to find in the packages, easy to solder, for example. No external RAM flash because, well, you have to route high-speed signals on your PCB board. It can be quite complex. As cheap as possible because the Raspberry Pi is 35 euros, so there is no point in making a lower board for 10 times the price of the Raspberry Pi. There makes no sense. So, and simply sourceable, you should be able to go to your electronic shop and get the component. Well, modern interfaces to be able to interface with off-the-shelf peripherals and simple to manufacture. So it was okay to use double-sided PCB, for example, which can be made at home or can be ordered quite cheaply. It's not okay to have a several-layer PCB for a 4-layer PCB or more. For SMD soldering was okay because it's possible to solder by hand. So TQFP kind of packages for chips were okay, not BGA, for example, which has extremely small bolts, and you quite need to have some specialized hardware to solder. So let's just have a look at different kind of consoles. On the left, we have the Xbox One type of hardware, which has 8-core CPU, 1.7 gigahertz, 8 GB of RAM, 50 gigabytes Blu-ray to get. And on the right, you have a tiny 2330 Pong console, which I've built once. So you have 128 bytes of RAM on this one, which is 70 millions less than the other one. 2 kilobytes of flash. Well, between the Xbox One, which is very powerful but quite closed, and quite powerful, yeah, and the tiny Pong, which is quite open but limited to one game, and quite small. There should be some intermediary spec. On the 8-bit side, the Nintendo, for example, had a almost 2 megahertz processor, 2 kilobytes of RAM, which is small. The cartridge were around 32K to 1 megs of RAM, and you output 256 to 24 pixels. The use box is another project of do-it-yourself console that has been made before by another guy. You can see that the specs are quite similar for 8-bit games, except for the CPU speed, which is almost 20 times more, and the fact that, of course, there is no dedicated GPU, because the NES had a dedicated GPU to render tiles and sprites on the screen. The use box doesn't have such kind, so everything is emulated in hardware. So you're trading specialized hardware for megahertz. Well, I was aiming for 16-bit, so Super Nintendo was what I was roughly aiming for in kind of look and feel of the games. You can see there that it's roughly similar to the preceding slide in that we're trading special GPU with sprites and types for higher megahertz. I use an ARM STM32, so ST microelectronics chip for that, which is quite powerful for a microcontroller because it has 182 kilobytes of RAM, which is quite small compared to some board that you might implement Linux on, but it's exactly the same level of RAM that you can have a Super Nintendo. The output, well, I will get back to the output, but it's kind of resolution. The native resolution is 600 by 480, which is what you're seeing right there, compared to the TV output of a Super Nintendo, for example, which is quite smaller resolution. But if you want for a game to look, well, somewhat acceptable on modern screen, you have to to get the resolution a bit higher, which is more demanding for your CPU. But apart from that, everything is quite on the same level, except that you're trading megahertz for custom hardware. And just as a bit of comparison, the Raspberry Pi, which I've, again, nothing against, is, as you can see, 1,000 times more memory, for example. There is a dedicated video core GPU, so we're not in the same league. We're maybe 100 times less powerful, a little bit less than that for the CPU, but for everything else, we're not in the same league than the Raspberry Pi. It's very simple, and it's more like a Super Nintendo kind of level of hardware. So first, the development was on the developing board, so quite cheaply. Here is the first powerful GPUs made of a bunch of resistors, and so everything was made, yeah, I don't know, you have here in the preceding slide for a grand total maybe of $20 of material. And finally, I managed to get some, to synthesize in real time the VGA signal. So being able to output an image was a kind of an accomplishment for the project, which is, it was not a moving picture. It was not a static picture, but the fact that, yeah, it was quite a nice accomplishment for the project. So currently, the Bitbox revision 2 has connects to two full-size USB hosts to be able to connect to USB game packs, for example, which are quite easily to find. The core, of course, the STM32F405. You get an external connectors and a stereo line out to the element, to the loudspeaker, or whatever you plug in the line out, and the VGA out with a 15-bit resistor DAC directly plugged in the STM32, which has, again, no GPU. There is nothing particularly tailored for video in this chip. It's just a general microcontroller, quite a generic microcontroller. There is nothing for outputting video or processing images, for example. Okay, and here is the, and here is the board. There is one there if you want to have a look. So you find the dual USB hosts, which are full-size USB to be able to plug it simply, not micro USB. There is a micro USB for power, the user button extension port, which I will get back to after that, reset button, audio out, and the VGA, the big VGA. You can see that most of the size is taken by connectors. So first, a little bit about the hardware. What's in a game console? Well, you need CPU, RAM, and flash. That's everything inside the microcontroller. That's taken care. You need to output video, make sound, handle input peripherals, have some masterage, and handle some games transfer. The chosen microcontroller was the STM32F4 with 1 megs of flash, so it allowed some more complex games. That very simple one that, well, you can begin to have some quite complex game. It costs around €7. Well, you have to buy 10,000 of them, but if you want, you can buy one, and it's I don't know, maybe twice that price, a little bit less. So well, we need, of course, everything to be always cheaper. Remember, Raspberry Pi, €35. Okay, so mostly that. How to generate a video signal? To generate a video signal, you just have to remember how it felt like 50 years ago to generate a black and white video signal from the TV. You have the beam, electron beam, which is getting from the top left to the bottom right in ranges of electrons. And you modulate the power of this signal with your signal. So if you go to 1 volt to get white, and you get to 0.3 volt to get black, and you make that change in time during the time, and during this time your beam is going from left to right, and then you have to go back to the left. So you are outputting synchronization signals back to 0 volts, that's the small dots there, element there, to tell the beam to get back. And there is some very simple circuitry, and it's a very nice hack to be able to produce images that way. That was the black and white, quite simple to understand, and it's the same thing today for black and white television. Or what about color? For color, you need 3 components: red, green, blue, basically, or since that would better fit with the ancient, and you have to be compatible with the black and white signal. So you send the luminance, and then you send for the composite signal for one for one. Sorry, I forgot the name. Well, merci. If you have to transmit everything in one wire, you transmit modulated color, which is quite complicated to achieve by yourself. If you want to recreate that, you can have a super video, for example, well, Luma, which is black or white, and chroma are separated, or you can have components Y and differences to the luminance, blue and red on 3 wires. But the most simpler thing to do, and the more ubiquitous plug to find, because you need to find screens to plug to, is a VGA, because for the VGA you have 5 elements: the synchronization, the vertical synchronization to tell the beam to go back up, the horizontal synchronization, red, green, and blue. Well, that's the 5 wires that you have on any VGA board. So it's very simple to generate a video signal. You just have to output those 5 signals in the right time separately. You don't have to you don't have to mix them into one wire, so it's quite easy. What's very important, of course, to generate a video signal, it's video timings. You have for one line, on the top there, it's one line. You have the sync signal, then you have to wait for around 50 pixels, then you have 640 pixels to generate, and that's one line, and then you have to do that again and again and again for each line. So you don't have, you cannot not be completely synchronized, because if you shift by 1 pixel, for example, so that's a very small amount of time, you will have a completely distorted image, and a very small number of time means that, okay, if you want to output standard VGA resolution at 60 frames per second, for example, that means 25 megahertz. So you have to generate a 25 megahertz from a 160 megahertz microcontroller. So that means that you have 7 CPU cycles to generate each pixels. And if you shift by more than 7 cycles, well, your image will be distorted. Okay. Here are the key features of the STM32F4 that will be used. I simplified a little bit this one. You use the GPIO of the microcontroller to output, of course, the signal. Use a DMA. There is a DMA inside. What's DMA, for those that you don't know them? A DMA is a small element of silicon that can output, that can copy some part of the memory to other parts of the memory. So you can prepare a buffer for one line and tell the DMA transfer it to the GPIO address in memory. And then, since it's a bit of silicon and it's not the microcontroller who does this, it's very precise in time. So you can go off and prepare the next line, prepare the next buffer line, and tell the DMA to output that to the GPIO. Then you're using the other elements that are within the microcontrollers, the USB, for example, because there is a USB controller inside, SDIO to output and to make the input and output for the SD card. Some digital analog converter for the audio. For the video, it's much too fast to output video, but for the audio, you could, of course, use this one. Yeah. Oh, sorry. What's happening? It's a demo effect, of course. Okay, let's reboot. Well, you can see that it's quite easy to reboot. Okay. Oh, going too fast. Okay. Okay. For the output, the signal output is output on 15 wires of your microcontroller. Then you have a simple resistive DAC, and then you output for each of the color, red, green, and blue, to the VGA signal. So it's very straightforward from the microcontroller directly to the VGA signal. Then, what about the sound? You have an internal dual DAC on the STM32F4, so it's quite very easy. You just output the wires. You go through some low-pass, high-pass electronic filtering in order to improve a little bit the signal, and then out to your line out. So it's very simple. As you can see there, you get your microcontroller pins there, left and right. You go to small filtering and output to the jack. Here is the connectivity of the USB. Yeah, you got the connectivity for the USB direct to the microcontroller. Then you add some connectors for the SD card there, directly to the microcontroller. A user button, just in case you have to reboot. Might happen. Some debugging port, some power adapter there, some two LEDs, one for power, one for user LED, just to be able to test if we can blink a LED. And then you have the whole, no, sorry, no, not the whole one. There is an expression port also, in order to be able to connect external gadgets to the console. I reused an existing specification of an expression port, which is named UX. Basically, there were two main possibilities. The Arduino Shield, it's big, but it's not very useful for that kind of microcontroller because, and that kind of board, because many of the existing Arduino boards are already inside. For example, for the Arduino, you get video output, which is inside, sound output, which is inside, SD card, for example. So, and it's big. So there wasn't much room on the board. So I opted for another one, which is a UX, an existing standard, where you just route a serial connectivity, SPI, I2C. There is a very simple connector. It's not at all proprietary. And there exists a lot of external things that you can buy and connect to the Bitbox. So I haven't tried to connect them for now because we were focusing on the Bitbox. But it exists, IRDR, Raspberry Pi, adapters for Raspberry Pi, LCD, Bluetooth, GSM, Wi-Fi, biofeedback. You can plug yourself to the Bitbox. Gyroscopic input thermometer, wind and choke adapters, etc. It's do-it-yourself ready because it's very simple. It's almost the whole spec that you have there. And it's available, it's very available. Okay, so you might not see it, but it's a summing up of everything we have seen before. And it's a whole hardware for the Bitbox. So it's very simple. We've just seen them in 10 minutes. So here is a PCB, which was rooted from the preceding elements, and the physical resolution. Now for the software. For the toolchain for that kind of microcontroller, generally there are proprietary toolchains, but I use GCC and GDB for ARM, for the bare metal compiler. So you can use GCC to transform your C to O file, a standard linker to generate ELF files, FOSDEM to extract from the ELF files the right binaries. It's very straightforward, and the make files generally maybe, I don't know, 20 lines long. It's very simple to redo everything by hand, or just to compile without any make file. It's very simple. You can use, one of the big things is that you can use GDB directly on the chip. There is an debugging port, and you can plug it using a third-party board, which can cost maybe 10 euros, to be able to do step-by-step execution on the console, to read everything in the memory, to load some elements to the RAM. So it's very nice because you can debug without having to resort to a LED blinking debug, which is quite painful. Now you have complete view of what's happening inside from your PC, so it's very nice to see step by step your code from what's happening within the microcontroller. So the developing can be done on Ubuntu or other elements, but on Ubuntu is very straightforward. Windows, some people ask me whether they can develop games from Windows. It's possible, and Mac, I don't know. So here is the software stack. You have the hardware, and you put your game binary on it, and you just run it. That was nice and fine. There is no operating system, of course. There is only one process. There is only one user. It's very straightforward. However, well, it's your game, but with your game, you have to set up the VGA DMA, for example. You have to set up the timers to be able to run your DMA. You have to initialize the clocks tree, because there are several clocks for several ports of the element. You have to have a USB stack with a USB HID parser if you want to parse events that are sent by different gamepads, for example. And you have to implement the SDIO interface to FAT32 to be able to read what's okay. Well, it's a little bit painful. Well, you can do it all by yourself, but you can also reuse some existing libraries. So the more fuller software stack uses some library for VGA, USB, sound, etc. I call this the kernel. It's absolutely not a kernel. It's just a set of libraries that you link to your game, or you can choose or not to use them. With an interface which is made available in only one bitbox.h C file. Everything is programmed in C. There is no assembly. Well, you can put some assembly, of course, in it, but everything has been programmed in C for now. The kernel, is a kind of API or an SDK, in fact, more than a real kernel. It's a small set of low-level drivers. Everything is compiled in-game, and there is no specific algorithm in there. There is no engine, there is no bleater, etc. It's very simple. You have two interfaces. The first one is fill the buffer. Here is the line you are on. Fill the buffer for that line, and then the engine will take care of putting that to the screen, or outputting that to the different elements, electronic elements to the screen. And then for the next line, you will be woken up again by an interrupt. So you just have to provide one method, which is a fill line, game line with a pointer to your buffer, and the same for the audio. And another one for what part of your game, which will be woken up every frame, every video frame, I don't know, to take care of the buttons of the user, for example, to move the different sprites on screen, etc. And that's it. So you have three functions to implement with that kind of API to be able to use the different elements. There is an HID parser and a simple interface to hide the complexity of the USB stacks, which maybe is the most painful element to reproduce if you want to throw everything out. For the rest, it's very straightforward. Well, I don't know, the whole kernel, maybe, I don't know, several hundreds lines of C. It's not maybe 1,000 max. So it's not very complicated. Okay, there is an emulator, which is not really an emulator. In fact, it's an implementation of the bitbox.h file on SDL. So you can test your game on your PC, and then you can port it and you can compile it for the bitbox. So it just you just call the high-level part of your game. You compile it for with the SDL backend, and you just run it on your PC to be able not to have to upload it each time for the on the device. What compiles and runs with Bitbox, so for your inside of the Bitbox, can be emulated generally as is. Everything is reproduced generally. You have to be careful with the reciprocal, of course, because if you have, I don't know, 4 cores with 2 gigahertz, well, it's easy to go overboard on functions and not to have enough CPU left on that very small device, and you have very small memory left. So just remember that you have 100K of memory to put everything in RAM. However, one guy has made a game just with the emulator. Send it to me, I compiled it, and it ran first time on the Bitbox. So it can happen that you can code directly with your PC and then you upload it to the Bitbox, or you just recompile it, and it worked first time. And it didn't have the device, but it ran first time for the device, which was very nice for him. And after that, he built a Bitbox itself. Okay, well, that's nonsense. Graphics compression is necessary. You don't have enough room in the whole memory to store one frame buffer. So when you've blitted the last line, you don't remember, the Bitbox cannot remember what it blitted on the beginning of the frame, or not even 2 lines before. So you cannot store graphics completely uncompressed within the box. You have to compress it. You have to compress it, and you need to be able to decompress it on the fly, line by line. So it's a few, I think it's 31 kilohertz per second. So at 31 kilohertz per second, you need to be able to output a line and decompress it. So you have only 7 cycles per PSEC to decompress it and run your game. So you have to compress, but you have to be clever, but not too clever for your CPU to compress everything on memory. 1 frame is almost the whole flash memory. And so if you want to make a photo frame with one photo, you can, but it's not very useful. You have to compress to do anything. It needs to be also simple to modify your image, because a game is a moving image answering to real-time events. So you need to be able to modify your compressed graphics to be able to output on screen. So, for example, it's very difficult to compress RLE, very simple one lens encoding compression. Instead of saying 20 pixel blue, you just output 20 and then blue. That's nice, but it's not very simple to modify online, because this compression is very static. So you need to find some ways to do that. There are several ones. For this, there are some other libraries that you can choose not to, which implement such kind of renderers. There are different uses and different solutions. First, there is the text mode, which is a simple way to compress an image made of text. You get, well, a standard text mode. You just write some characters to a bunch of RAM, and the kernel and the different subsystems take care of everything. So you can start with that to develop with a Bitbox. There are other modes with a graphical frame buffer. So there you have to reduce something. So generally you reduce either the resolution or the number of colors on screen with the palette. So either you use a palette or you decrease the resolution, generally both. You can go up to 800 by 600, by the way, but there isn't much to do if you go like that. And then there's 2D engine, which I go back to, with tiles. So a tile engine made in software and with sprites blitting, which is the most useful to make games, but the other one can be useful to make some more smaller games. So you define different in C different objects, and you instantiate and move them on screen, and the blitter takes care of outputting that to the different lines of output. Then, sorry, okay. Sound engines, there are also sound engines. If you don't want to output everything by hand, well, there is a simple mixer sampler to play and resample audio from Flash, for example. So you just put in your Flash some notes and some music, and you tell the sampler to mix everything and to change the sampling rate on the fly to be able to output notes and music and special explosions. And well, you can import MIDI files as static files within this engine. There's also a mod file player, like the old tracker mod files. Maybe you do remember those ones. And there are other simple things for Square and more chiptunes like sounds. If you want to make some games, someone contributed simpler chiptunes like sounds and a synthesizer, and there is a tracker inside it. So here is a more fuller software stack with different layers, which you can get completely rid of and program from scratch, of course. One of the fun things, well, the project is trying to do something with a hardware that isn't made for. So I tried to have full motion video, to be able to run video full screen at a live speed. So you need to store one frame in RAM. You cannot do inter-frame compression because you cannot remember the past frame, so you have to keep one frame in memory each time. So I developed a more new codec, which well, allows to have some crude quality output video with 2 bits per pixel, which makes it fit in a whole full screen. So you can store that, and then you stream 64 kilobytes per frame to output video on the fly. So yeah, there is a Python encoder, which is very slow and very low quality. As you can see, the presentation has been compressed with that codec. Here is some, yeah, so that is a kind of picture that you can output with the Bitbox and with that kind of encoder. So you have to reduce the resolution, you have to reduce everything, so you have to be quite clever in how you, and you have to be fast to decompress because you only have 7 here. Yeah, you have to decompress everything on the fly, and when you're writing this one to the screen, you have completely forgotten that you've just decompressed the lower part of the image, for example. You redo everything every time. So there's some example pics, for example. Yeah, and there is a video example, but maybe I have time to show it. The program transfer can be done through the internal the bootloader from the chip, but you have to transfer it, it's quite slow. So I made a bootloader within the chip. So to be able to transfer, and you've seen it, to be able to transfer the program from the SD card. However, a bootloader has to be resident, it's only on chip. You don't have much room in the chip to store it generally. It has to be small, and it has to be stable and safe. You don't want to update the bootloader every time there is new version. However, selecting a file on screen with Gamepad and loading them from the microSD to the flash, it's quite a complex task, in fact, because for the console, at least, because you have to use FAT, SDIO, USB, VGA, flash programming, output of the text on screen, so you have to a font, a graphical font to be included, etc. So it's quite big. And then another small thing is that you cannot run from flash if you want to program the flash. So there was a problem. So the bootloader is in 2 stages. The first one is always inside, very small. It just knows how to load the second stage bootloader to RAM, and then from the RAM, well, it's a normal program. It's just running from RAM except from flash, and then you can program the flash. And this one can be complex, it can be updated, it's just a file on the micro SD card. Some examples of programs. There is a port of GNU Boy, which is a Game Boy emulator. So you can run this emulator on the Bitbox. So you can emulate 8-bit engines on this 32-bit CPU. You have to well, remove much of the functionality for game saves, for loading games from the SD card, for example. Everything of that has been removed, but you can keep working games. You can make Mario and Metroid Game Boy working. Well, there is much to do, but you can do. You can run those games. Of course, only freeware games, because you have to embed them into Flash, so it's difficult to do that with normal games. Yeah, here are some game screenshots, and there is a small menu to select them at boot. This one is the Bitbox to produce some battery sounds with the microcontroller. So you select different paths, and it runs some sounds to make some rhythms. There is yeah, small games like that. Much of the effort has been put into making the whole thing work and making it simple to be able to work. So the games, hopefully, are coming. There are several ones coming. This one is Boulder Dash demonstration. Yeah, well, it's a screenshot, this one, but yeah. There are other games in softwares. There are 248 because it's quite simple. There is Crappy Bird, which is a Flappy Bird, but very crappy one, which is well, it's an example to show how to do a very simple game without the engine. So everything is bare, everything's from scratch, and it's maybe 100 lines of C running directly on the Mitchell, not using USB connector, using the button to run. It's very, very simple. There are many well, yeah, there are some utilities, video players, SDK examples. There are many examples of the SDK. USB device tester yeah, because it's quite complex to handle the different gamepad, keyboards, and mouse differently. So there is a small tester for that, so some of that, and many of them have been contributed by other people for this one. There are many, and too much for the times of the different people there. In progress games, some shoot them up, so video-based adventure, a beam racer, which is kind of a racer outrun, maybe, but it's a play on word with racing the beam, which is the fact that you're racing, the fact that the electron beam, you have to produce the image. That's an expression that you found in old consoles. There's Bombleman and Shadow of the Bit. Yeah. What about the future? Well, first, make games. Improve, of course, the emulator, improve the engines, different engines, make them smarter or more compressible. But to make a game, you need to produce graphics, you have to produce sounds, you have to produce interesting gameplay, for example. Debug everything, of course. Improve the kernel on the engine. Maybe do some more 8-bit simulators. NES should be quite doable. ZX Spectrum, Sinclair, Wildix Spectrum with a keyboard I think can be done with a basic, maybe. Playing with extensions. One of those that I would like to play with are Wi-Fi and nunchucks, because there is an accelerator, so it's quite can be fun. And Wi-Fi, well, the SP8266 chip is very inexpensive Wi-Fi component that you can add to your project. I don't know, it's maybe $5 to have Wi-Fi, so it can be interesting to use them to add multiplayer games. But not more powerful hardware, because that's the whole point, is to have the limited but stable hardware. Yeah, that's it. A small number of links. The first one is the main blog, where the whole development process has been presented, and there are tutorials from time to time presented. And the GitHub part, where everything is detailed, and the source code of everything, and the files to be able to replicate this console by yourself are present also. That's it. Do you have any question? Yeah?
Are you expecting a thriving demo scene on your console?
I'm not expecting this. I'm hoping for this, but yeah, why not? Yeah. No, but I prefer to focus on games, but and I'm trying to make some libraries to ease the development of games. But yeah, there have been some demos with that chip. Not the console, but the chip itself. There have been some demonstrations. Oh yeah, sorry. Sorry, excuse me. Come on, sorry. Can you play? Yes, of course, please. Please do. Let me check. I have a simple game there.
Yeah, while some people play, well, when you're leaving, please try to take some trash with you and throw it in the trash
Jumper.
bins.
Yeah.
Thank you very much and see you next year.
It's writing. Now, the bootloader here is loading the program from the SD to the flash. So it's writing. It's quite big. Okay, that's down. Not now. No. Could be interesting to test because the parser is handmade. So I don't know if, yeah. I have no idea if it runs standard HID. Okay, but then, it runs to the left, but not to the right. I don't know why.
Can I take a picture?
Of course, you can.
Reboot again.
That's my, I don't know what's happening with this. I cannot go to the left. That's, this one cannot go to the left. I don't know what's happening. Okay, it's a game where you can do, let's try another one. Sorry. That way, to load the bootloader, you have to press a button. Those are very simple games because there hasn't been much time to. Fireman, let's try this one. This one is very simple. It's one of the earliest ones. Don't know if you remember this one. So it's running 60 frames per second. My pad should be.
Maybe the pad is broken.
My pad seems to be broken. You cannot go to the left. So maybe we can try with your pad. It's broken. Okay. I don't have much hope for this to run for the first time, so I'm not hovering my.
Can you do the other one?
No, because the game has been programmed to run on this one. So, is it working? Yeah! Woohoo! And can we go to the left? Yes, we can. Okay. Well, this one's very simple. It gets harder, but do you want to try? Do you want to try? No, you have the wrong one. Yeah. At 20, I think you have 2 guys, and then you have 3 guys in problem.
Very nice, thank you.
No, not on this game. No. Oh, sorry.
Can I look?
Sure, please do.